Hello everyone. Today we are going to analyze this beam using stiffness matrix method. Before analyzing, let us see the beam one time. In this beam, there are two spans, span BC and span CD. Also, there are two overhanging spans. On the left side, we have a overhanging span AB. On the right side, we have a overhanging span DE. So we have overhanging on both of the sides. In the overhanging AB, we have a point load 30 kN in the point A. In the span BC, there is a point load 20 kN acting in the center. In the span CD, there is UDL 12 kN per meter acting for the full span. In the overhanging span DE, we have UDL 12 kN per meter. In this analysis, we have to find totally 6 moments. In the joint B, we have to find MBA and MBC. In the joint C, we have to find MCB and MCD. And finally, in the joint D, we have to find MDC and MDE. So, totally, we have to find 6 moments. Also, we have to calculate 3 reactions RB, RC and RD. In the joint B, we can easily calculate the moments MBA and MBC because there is overhanging on the left of B. To calculate MBA, we have to multiply this load with the overhanging distance. When we do that, we are getting 60 kN meter. MBA should be positive because it is acting in the clockwise direction. MBA and MBC will have the same values, but the sign only will be different. MBA should be positive because it is acting in the clockwise direction. MBC should be negative because it is acting in the anti-clockwise direction, but both of the values will be same. In this concept, we can calculate MBC. Just we have to change the sign of MBA. So for MBC, we are getting minus 60 kN meter. In the same way, we can calculate the moments MDC and MDE in the joint D. To calculate MDE, we have to multiply the UDL with the overhanging distance and a distance by 2. We know that when the UDL comes, we have to multiply with the distance and a distance upon 2 to find the moment. Here we have to be very careful. MDE is acting in the anti-clockwise direction, so we have to apply the load with the negative sign. That is why we are getting a negative moment. The values of MDC and MDE will be same, but they will have the different signs. MDE is negative because it is acting in the anti-clockwise direction. MDC should be positive because it is acting in the clockwise direction, but both of them will be having the same values. In this concept, we can calculate MDC. We have to just change the sign of MDE. When we do that, we are getting MDC as 54 kN meter. Now, let us calculate the fixed end moments. We don't have to calculate the fixed end moments in the overhanging spans. Only we have to calculate them in the spans BC and CD. Let us calculate the fixed end moments in the span BC. In the span BC, there is a point load 20 kN. It is acting in the center. The formulas to calculate the fixed end moments are minus WL upon 8 and positive WL upon 8. Let us apply the values inside the formulas. W is 20, L is 4. When we apply the values, we are getting M of BC and M of CB. Now, let us make the fixed end moments in the span CD. In the span CD, there is UDL 12 kN per meter. It is acting for the full span. The formulas to calculate the fixed end moments are minus WL square upon 12 and positive WL square upon 12. Let us apply the values inside the formulas. W is 12, L is 4. After applying, we are getting M of CD and M of DC. In the stiffness matrix method, we have to check the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. In the roller support also, there will be slope. In this beam, in the points B and D, there are hinged supports. In the point C, there is a roller support. So, the number of supports where slope occurs is 3. In the point B, there is theta B. In the point C, there is theta C. And in the point D, there is theta D. In this analysis, there are 3 unknowns. If we calculate these 3 unknowns, we can easily find the final moments. Now, let us make the fully restrained structure. In the fully restrained structure, there will be no slope. We know that only in the fixed support, there will be no slope. So, let us remove the hinged supports from the point B and D, and also the roller support from the point C, and replace them with the fixed supports. Now, in this structure, in the supports, there will be no slope. That is why it is called the fully restrained structure. In the fully restrained structure, no need to consider the overhanging spans. We have made the fully restrained structure. Now let us make the coordinates diagram. In this analysis, there are 3 coordinates. They are in the points B, C and D, because in these points only we have slope. The coordinates should be made in the clockwise direction. You can see that all of the 3 coordinates are in the clockwise direction. Now let us see the formula to calculate the slope values. System displacement delta matrix is equal to K matrix inverse into P matrix minus PL matrix. Inside the delta matrix, P matrix and PL matrix, we will have 3 values because in this analysis there are 3 coordinates. Inside the delta matrix, we will have the slope values theta B, theta C and theta D. In this formula, first let us find PL matrix. We know that PL matrix is the moments developed in the coordinates due to the given load. In this analysis, there are 3 coordinates. In the point B, in the point C and in the point D, there are the coordinates. The PL matrix should be calculated in the order first from the first coordinate, then from the second coordinate, finally from the third coordinate. In the point B, we have calculated a fixed end moment M of BC. Let us apply that. In the point C, we have calculated 2 fixed end moments M of CB and M of CD. Let us add both of them. After adding, we are getting minus 6. In the point D, we have calculated a fixed end moment, that is M of DC. Let us apply that. In this way, we can easily make the PL matrix. In this formula, now let us make the P matrix. We know that P matrix is the final forces or moments acting in the coordinate direction. P matrix should be calculated in the order first from the first coordinate, then from the second coordinate, finally from the third coordinate. Let us take the first coordinate. In the joint B, we have calculated 2 final moments, MBA and MBC. Here we may have some confusion which moment we have to apply inside the matrix. MBA is acting in the overhanging span, so we should not select that. MBC is acting in the span BC, so we must select this. MBC is minus 60. Let us apply that. Now let us take the second coordinate. In the second coordinate C, we did not find any movement. Due to the overhangings, there was no movement developed in the point C. So in the second coordinate, we have to enter 0. Now let us take the third coordinate. In the point D, we have calculated two final moments, MDC and MDE. MDE is acting in the overhanging span, so we should not select that. MDC is acting in the span DC, so we must select that. MDC is 54. Let us apply that. In this formula, we have found the PL matrix and P matrix. Only one is remaining, that is the stiffness matrix. Now let us see how to calculate stiffness values inside the stiffness matrix. For that, we have to apply unit displacement in every coordinate. In this analysis, there are three coordinates. In the point B, C, and D, we are having the coordinates. In these coordinates, we have to apply the unit displacement. Then we have to use the formulas. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged, the formula is 2EI upon L. Here we have to be very careful. We have to apply the unit displacement in the fully restrained structure and not in the given beam. Now let us see the size of the stiffness matrix. For 3 coordinates, the size will be 3 cross 3. For 2 coordinates, the size will be 2 cross 2. For 1 coordinate, the size will be 1 cross 1. In this analysis, there are 3 coordinates, so the size will be 3 cross 3. In the stiffness matrix, now let us calculate the first row. For that, we have to apply unit displacement in the first coordinate. In the point B, there is a fixed support, but when we apply unit displacement, it is no longer a fixed support, it becomes a hinged support. Because in the fixed support, there will be no displacement. Now let us see how to draw this curve. We are applying unit displacement in the point B. So in the point B, we have to make a clockwise curve and then we have to see the direction of the arrow. This arrow indicates downwards, so the curve comes below the span. We have to give some gap between the fixed support and the curve because in the fixed support there will be no slope. You can see that I have given some gap between the fixed support and the curve. That is why the curve ends before the point C and can't continue after the point C. Same like here, the ordinates should be made in the clockwise direction. Now let us calculate the stiffness values. The stiffness values should be calculated in the order, first from the first coordinate, then from the second coordinate, then from the third coordinate. Now let us calculate K11. For that, from the point B, we have to look on both the sides. On the left side there is nothing. On the right side there is a fixed support. If the fair end is fixed, the formula for stiffness is 4EI upon L. Length of BC is 4 meter. Let us apply that. Finally, we are getting EI. Now, let us calculate K12. For that, from the point C, we have to look on both the sides. On the right side, there is no curve. If there is no curve, there will be no stiffness. On the left side, there is a hinged support. If the fair end is hinged, the formula for stiffness is 2EI upon L. Length of CB is 4. Let us apply that. Finally, for K12, we are getting 0.5 EI. Now, let us calculate K13. For that, from the point D, we have to look on both the sides. On the right side there is nothing. On the left side there is no slope curve. In this case there will be no stiffness. K13 will be equal to 0. In the stiffness matrix, now let us make the second row. For that we have to apply unit displacement in the second coordinate. In the point C, there is a fixed support, but when we apply the unit displacement, it is no longer the fixed support, it becomes a hinged support. Now let's see how to draw this curve. We are applying unit displacement in the point C. The point C is a joint. It is connecting the spans CB and CD. So we have to make two clockwise curves. One curve towards the point B and one curve towards the point D. Then we have to see the direction of the arrows. This arrow indicates upwards, so the curve comes above the span. This arrow indicates downwards, so the curve comes below the span. Now let us calculate the stiffness values. Let us calculate K21. For that, from the point B, we have to look on both the sides. On the left side there is nothing. On the right side there is a hinged support. If the fair end is hinged, the formula for stiffness is 2EI upon L. Length of BC is 4. Let us apply that. Finally, for K21, we are getting 0.5 EI. Now let us calculate K22. For that, from the point C, we have to look on both the sides. On the left side, there is a fixed support. If the fair end is fixed, the formula for stiffness is 4EI upon L. Length of CB is 4. Let us apply that. Now let us look on the right side. On the right side also, there is a fixed support. So we have to apply the same formula 4EI upon L. Length of CD is 4. Let us apply that. For K22, we have to add these two values. After adding, we are getting 2EI. Now let us calculate K23. For that, from the point D, we have to look on both the sides. On the right side, there is nothing. On the left side, there is a hinged support. If the fair end is hinged, the formula for stiffness is 2EI upon L. Length of CD is 4. Let us apply that. Finally, for K23, we are getting 0.5 EI. In the stiffness matrix, now let us find the third row. For that, we have to apply unit displacement in the third coordinate. In the point D, there is a fixed support. But when we apply the unit displacement, it is no longer a fixed support, it becomes a hinged support. Now let's see how to draw this curve. We are applying unit displacement in the point D. So in the point D, we have to make a clockwise curve towards the point C. Then we have to see the direction of this arrow. This arrow indicates upwards. So the curve comes above the span. We already know we have to give some gap between the fixed support and the curve. You can see that I have given some gap because in the fixed support there will be no slope. That is why the curve ends before the point C and it can't continue after the point C. Now let us calculate the stiffness values. Let us calculate K31. For that, from the point B, we have to look on both the sides. On the left side there is nothing. On the right side there is no slope curve. So the stiffness value will be 0. Now let us calculate K32. For that, from the point C, we have to look on both the sides. On the left side, there is no slope curve. On the right side, there is a hinged support. If the fair end is hinged, the formula for stiffness is 2EI upon L. Length of CD is 4. Let us apply that. Finally, for K32, we are getting 0.5 EI. Now, let us calculate K33. For that, from the point D, we have to look on both the sides. On the right side, there is nothing. On the left side, there is a fixed support. If the fair end is fixed, the formula for stiffness is 4EI upon L. Length of CD is 4. Let us apply that. Finally, for K33, we are getting EI. In the stiffness matrix, we have calculated all of the rows. Let us apply them. EI is constant. Let us keep it outside. In this formula, we have calculated all of the values. Let us apply them. Let us make inverse of EI and take it outside. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to find inverse in the calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and found the inverse. Then we have to add these two matrices. After adding, we are getting this matrix. Then we have to multiply these two matrices. After multiplying, we are getting the final answers. In this analysis, we have calculated the unknowns. Now we can make the slope deflection equations and find out the final moments. First, let us make the slope deflection equation for MCB. In this equation, let us apply the fixed end moment. Length of CB is 4. Let us apply that. After applying the values of theta B and theta C in the equation, we are getting MCB, which is equal to minus 9 kilonewton meter. Now let us make the slope deflection equation for MCD. First, let us apply the fixed end moment. Length of CD is 4. Let us apply that. After applying the values of theta C and theta D, we are getting MCD, which is equal to 9 kilonewton meter. For MBA, MBC, MDC and MDE, we have already calculated the final moments, so no need to make the slope deflection equations and waste the time. In this analysis, we have calculated all of the moments. For MCB, we got a negative value. That means MCB is acting in the anti-clockwise direction. For MCD, we got a positive value. That means it is acting in the clockwise direction. Initially, we assumed that MCB would be acting in the clockwise direction and MCD would be acting in the anti-clockwise direction. But our assumption is wrong. MCB is acting in the anti-clockwise direction and MCD is acting in the clockwise direction. Now let us calculate the vertical reactions. Let us take the overhanging span AB and the span BC together and calculate the vertical reactions. When we take them together, no need to consider MBA and MBC. They will get eliminated. Only we have to consider MCB, which is acting in the anti-clockwise direction. In these spans, first I am going to calculate RB. For that, I am going to take moment about C. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. The point load 30 kN is acting towards the point C in the anti-clockwise direction, so it will be negative, and the distance is 6 meter, so minus 30 into 6. RB is acting towards the point C in the clockwise direction, so it will be positive, and the distance is 4, so 4 RB. The point load 20 kN is acting towards the point C in the anti-clockwise direction, so it will be negative, and the distance is 2 meter, so 20 into 2. Finally, there is a movement which is acting in the anti-clockwise direction, so it will be negative. After the calculations, we are getting RB, which is equal to 57.25 kN. Now let us apply the rule sigma V is equal to 0 and calculate RC1. For RC1, we will get a negative value. That means our assumption is wrong. We assumed that RC1 is acting upwards, but actually it is acting downwards. Now let us take the spans CD and the overhanging span DE together and calculate the vertical reactions. When we take them together, no need to consider MDC and MDE, they will get eliminated. Only we have to consider MCD, which is acting in the clockwise direction. In these spans, first I am going to calculate RC2. For that, I am going to take moment about D. RC2 is acting towards the point D in the clockwise direction, so it will be positive and the distance is 4 meter. So for RC2, then we have to take the UDL. We have to split the UDL into two parts. First in the span CD, then in the overhanging DE. In the span CD, it is acting towards the point D in the anticlockwise direction, so it will be negative. When the UDL comes, we have to multiply the load with the distance and distance upon 2. Now let us take the UDL in the overhanging DE. It is acting towards the point D in the clockwise direction, so it will be positive and the distance is 3. So 12 into 3 into 3 upon 2. Then we have a moment which is acting in the clockwise direction, so it will be positive. Finally, we are getting RC2, which is equal to 8.25 kN. Then let us apply the rule sigma V is equal to 0. Using the rule, let us calculate RD, which is equal to 75.75 kN. Now let us add RC1 and RC2. After adding, we are getting RC. Now I am going to calculate the shear force values. I am going to start from the point A and move towards the point E. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. Using that, we can calculate the shear force values. Using the values, we can make the shear force diagram. Now, let us make the free movement diagram. Now, let us make the end movement diagram. Using the direction of the movements, we have to make the end movement diagram. If the end movement diagram comes above this line, that will be negative. If it comes below the line, that will be positive. So here it is negative and here it is positive. Now let us combine the free movement diagram and end movement diagram so that we are getting the bending moment diagram. Now we are going to end this session. Thank you for watching this video.